example 10.3.1. I have corrected its explanation so that it is a bit more understandable and those confusions are removed. Now, this is the equation that we are given in this example. You can see here, this example is from the book. Alright, so we try to understand this example of 10.3.1. So it says that we have binary PAM, alright. So PAM could be +1 and -1. Data rate is 1 over T bits per second. Bandwidth of the channel is W, and the output that we receive at the match filter is given as follows. So this is what I've written in my corrected note. So this is the output that we are getting. Here you can see that we actually needed just A of M. For the mth sample, sampling time, MT, you needed only AM, but you're also getting these two ISI terms. If I compare this equation with the general equation of the required and the ISI terms which we have given in the last lecture, you can very well see that this AM corresponds to this AM, right? So there has to be x0 here, x0, this means that x0 is equal to 1. While this summation, it corresponds to these two terms, alright? Now what can I do, how can I open up these terms is that, so I know definitely this is AM minus 1, but I know AM minus 1 means n is equal to minus 1. So n is equal to minus 1 means it becomes minus m plus 1, and hence this will become xm minus m plus 1. Similarly, am minus 2 means n is equal to m minus 2. This becomes m minus 2, mm cancels, and you have plus 2. Mm cancels and you have plus 2. The other term, the Gaussian white noise term, remains the same. Now, you can cancel these mm's and mm's, so this will become am x0, am minus 1 x of 1, and am minus 2 x of 2 plus w1. Now I can compare this equation with this equation, and hence I will get x0 is 1, x1 is equal to 0.2, x2 is equal to minus 0.3, and wm is just wm. This is why I will get these values. Alright, so what are these values? We know these are the overall response. These are the x. What was x? X was the convolution of the overall channel response convolved with a match filter. What was the overall channel response? That was the convolution of the channel response with the with the transmit function, or with the signal that was transmitted. It was convolved with the channel. You got h of t, then h of t was convolved with the the match filter, and then finally you got this x. So we have now found these values of x, and all other x for all other values m, this is 0 because only there are two terms for the ISI. Now when will the peak value of ISI occur? Peak value of ISI occur when these two values are added. For you can say that am minus 1 is equal to minus am minus 2. In that case, both of them will be added. Okay, or you can make other combinations. So worst case will happen when one of the worst cases will be the am minus 1 is equal to am minus am minus 2. This will become minus am minus, is already minus am minus 2. They both will add, and ISI term will come out to be minus 0.5. So if I say that this am, let us say, is 1, this is also 1. The symbol which was sent 2 time slots before is also 1. So you can very well see that the signal will be distorted by, or its amplitude will be decreased by 50% of its original value. Hence the noise margin would have reduced by 50%, or you can say the I would have reduced by 50%, right? So this is what is written in the book also here. Noise comp now, so a noise component which is even 50% smaller, that can cause an error at the detector because their margin is reduced by 50%. If there is a noise which is greater than 50%, you know that signal, if it was negative, it will go positive, and hence you will be detecting the wrong signal. Last lecture we saw. So these are the two levels of the PAMs. So this is reduced, let us say from here to here, and then a noise comes which can move it significantly here. So you will be detecting this symbol rather than this symbol. This is the overall. So we can see we have ISI. You always have ISI in these limited channels, band limited and LTI channels. And how can we uh, deal with them? How can we remove their effects? And what should be done? So there are actually uh, two ways of designing our signal, or we can resolve our problem signal design in two ways. One way is that we allow no ISI to occur, and the other is that we allow a controlled amount of ISI or intersignal interference to occur. We go with the first design, the design of band limiter signals for zero ISI. So we don't allow any signal, any ISI to exist. We have already seen XFT is convolution of the response, the total response, the channel convolved with the match filter that we have studied, and this HFT is the response of the transmit filter with the channel response. In frequency domain, we have seen it like this, and for zero distortion, we said that C of F is just band limited to, let's say, a W bandwidth, and within that bandwidth, it has this response, constant response, and phase is linear. And we said the C naught is 1 and T naught is 0. So we got total XFF is GTF into GRF. This we have already studied in the last lecture. And even for this response, we saw that Y of M comes out to be like this. So it has an ISI term. If I want to remove this ISI term, so I have to have this ISI term equal to 0. Now when this will be possible? This will be only possible if, because you know AN, these are the PAM symbols or the symbols QAM or PSK which are being sent. You cannot reduce them to 0, but you can reduce this channel response. This is the total response of the match filter, of the channel, of the transmitting filter. Everything is included here. We would like to have this equal to 0 for all those values where this is not 0, because for x0 we need it to be here non-zero, but for all other values where you know this factor is not 0, okay, or this bracket is not 0, we would require the overall function to be 0. So in this way, for all non-zero values of m minus n, you can very easily they are 0. Once they are 0, then means all of that ISI comes out to be 0. So you can also write this condition as that for n0 you have x naught, and for not 0, for any other non-zero value, you would like to have it to be 0. You can further assume that this x naught is 1, so that we have normalized our response. So overall response would be that for n0 you would have 1, and for any non-zero value, any other non-zero sample time or sampling interval, your value of xn will be 0. So we can also go from the book explanation, but I found many steps are missing in the book, so it becomes difficult to understand. That is why we are switching to notes for understanding this. So what should be the necessary conditions? This is a condition on as sample version of XFT, but what should be the necessary condition on XFF? So that X of NT can satisfy this condition, and this condition is called the Nyquist pulse shaping criteria or Nyquist criteria for zero ISI. XFF will definitely have some XFF, the frequency response. So we will see that the Nyquist criteria comes out to be for this amount of x of t. The Nyquist criteria comes out to be that the frequency response, which is replicated at 1 over d in frequency, comes out to be a straight line of value t. Uh, we will be doing it smooth, but just for explanation, this is what we want. We want your XFF to be a straight line, all right, and the value should be t. This is what we want of our XFF. We will be just understanding this derivation. All right, so you want XFF, and it's it's periodic versions plus XFF. Periodic at 1 over t comes out to be t. This is what we want. But if this is satisfied, then you will see that you will have zero ISI. But first of all, we have to see how can we prove this term and how this satisfy our Nyquist criteria. So we all know x of t, the inverse Fourier of x of f, then x of nt. So we sample t at integral multiples of the sampling time. So wherever there is t, you replace it by nt. Now here I am writing the same integral into summation of intervals, where each interval is of length of 1 over t. So what I've done, I've broken up the integral into small integrals of length 2m plus 1 minus 2m plus 1 over 2t minus 2m minus 1 over 2t, and you can solve. This comes out to be 1 over t. So I've broken this long integral into subintervals of 1 over t. Now we apply change of variables or substitution method. So we say f is equal to f dash plus mt. F is equal to f dash plus mt. This means that f dash can be written as f minus mt, and you can see df dash will be equal to df. So xf will now become x of m dash plus mt. What will happen to the limits? The first limit was at 2m plus 1 over 2t. The new limit for f dash will become, after change of substitution, will become 2m plus 1 over 2t minus m over t, because f dash is equal to whatever the value of f minus m over t. Whatever the value of f minus m over t. So I take its LCM. This becomes 2m, 2 and 2 cancels, and you can see f dash comes out to be equal to 1 over 2t. Similarly, f dash for the other limit, which is 2m minus 1 over 2t, you can raise this become minus 1 over 2t. So f dash will become minus 1 over 2t. And so minus 1 over 2t to plus over 2t, f dash plus fmt, this value. And as you change this, the exponential term will also be affected. So we will replace this f by f dash over nt. So one will be ej2 pi f dash over nt, by another symbol will be ej2 pi m over t nt. Comes out to be mt over nt. This ct cancels, this ej2 pi mn. M is an integer, n is an integer, so this product will also be an integer. So any integral multiple of 2 pi just goes to 0 power phase 0, or you can say cos E of J0 will be equal to 1. So we will be left with this term. There, these are here. Here this term I say is equal to ZF dash. ZF dash comes up to this thing. So dash has replaced this value. So you can say that ZF dash is equal to summation of XF dash plus MT, and ZF dash is actually XF dash, but it is a periodic extension of XF dash by 1 over T. So time period of ZF dash will be 1 over T. It is just XF dash in one time period. Another time period is being just repeated here 1 over T. So if ZF dash is XF dash with period 1 over T, this means periodic, and as a periodic we have Fourier series coefficients. So we can write this as follows. There is Fourier series coefficients, and we know how to write the Fourier series coefficient of a periodic signal. So here are the Fourier series coefficients of this signal, and you know EJ2 pi FT, F is F dash, EJ 2 pi F N T, and that is the periodicity. The periodicity is 1 over T. So 1 over T here will come out to be T in the numerator. ZF dash comes out to be Zn EJ2 pi F dash and T. Previous was T0, so T0 is replaced by 1 over T, because 1 over T is the time period, and previously the signals we used to find the coefficients. In the time domain here, these coefficients are in the frequency, because you can see that the signal is periodic in frequency. So that is why we have written the Fourier series coefficients in the frequency domain, which is here. Over here it is F dash. Mani, is there any understanding how this has happened? Alright, any student has any question with this? Mani, Zoha Ikram, Zoha Khurram, have you understood this thing? Kamil Javed, have you understood? Sure. Alright. So again, you can just revise your Fourier series coefficient, so you can write a periodic signal. That periodic signal could be periodic in time, it could be periodic in frequency. Here it is periodic in frequency. That is why we are using the appropriate notation in terms of F. So F will be equal to this thing. And we know these Fourier series coefficients, they can be found from the actual signal, which is in F as ZF dash E minus J2 pi F dash and T, negative of this thing. And the limits, they will be going from the time period So z of n will be equal to 1 over the periodicity or the time period where it is being periodic, which is 1 over t in frequency, and then this is the interval, because 1 over t is interval, so we will be integrating from minus 1 over 2 to dt. Zf is the signal frequency, e minus j2 with this plus will become minus, and we will be integrating in. Now if you compare this C equation with V equation, which was this, so you can very well see that Zn is equal to x and t, but because there is a negative sign there, so it will be x minus nt, and this t also here. So Zn can be written as x of minus nt, and along with this t, so this Zn is equal to t into x minus nt. So Z of n will be equal to t provided n is equal to 0, and we know that x of 0 is actually 1, comes out to 1, and Z of n is equal to t. For other values of n not equal to 0, we know that our x will be 0, and hence Z n will also be equal to 0. Now we can substitute the value of Zn in equation D. So you can see Zn is t for n is equal to 0. For all values of n, it is 0. So it will just be t into ej2 pi f dash n 0. So it will be just equal to t. So zf will be equal to t. But we have already seen that zf dash is equal to periodic extension of x of f dash. This we have seen already there. Zf dash is equal to periodic extension of x of dash. So if zf is equal to t, so we can see this periodic will must be equal to t for 0 ISI. So this is the condition for 0 ISI, and this condition we have proved. Now we have proven this equation, but what is the practical realizability of this equation? Because any signal x of t or its Fourier x of f, if it satisfies this equation, especially, then only we will have 0 ISI. So in time domain, we have seen that x of 0 is equal to 1 while all other x's are 0. And in frequency domain, we have seen that the spectrum must be of constant height t. So again, we assume we have a channel which we say is band limited to W frequency, so it is 0 above this W, and so if CF is 0, this means definitely that x of f will be definitely 0 for f greater than 0, because x of s comes out to be the multiplication of C of f with GTF and with the match filter. So if CF is 0, then definitely this is pure multiplication, so x of f will also be 0 for f greater than W. So this means we will have 3 cases. The cases are also discussed in the book here after. So these are the 3 cases. Again, I think it is better to switch to the notes because of some steps being missing. Now, what will be the first case? The first case will be that your t is less than 1 over 2w, or in other words, 2w is less than 1 over t. Remember that 1 over t is the the periodicity of x of f. X of f is repeating by 1 over t, and w is the bandwidth of your signal. So if your periodicity or your repetition is greater than your uh, bandwidth is w means bandwidth of one w, and then the other w bandwidth of the other replica. So if 1 over t is greater than 2w, then this means that you will have gaps in the spectrum, this spectrum where you have replicated x of f. You are replicating, but there will be gaps, and hence you won't be able to satisfy the condition of constant value of z of f, which was required to be equal to t, because you will have non-overlapping replicas of x of f, which will be separated. For example, you can see this was your, let us say, x of f going from minus to, so random to w, right? And this is your replica of this thing, but this is replicated at 1 over t. And you can see that this 1 over t is greater than this w plus w. This is also w, this is also w. This 1 over t is greater than 2w. So you will have this much band where you have no response, and it is not satisfying the condition of height of t. It is only satisfying in this range it is not satisfying. That is why we under these conditions, that your 1 over t or your uh, is greater than 2w, 1 over t is greater than 2w, you cannot satisfy Nyquist criteria, hence there will be ISI in these systems. Now what will be case 2? In case 2 we say, alright, t is not greater than 1 over 2w, rather t is equal to 1 over 2w. So you can see, or you can say that 2w is equal to 1 over t, or we can say that w is equal to 1 over 2t. So in this case, you can see is 1 over t, so w is equal to 1 over w will stand exactly at the middle of 1 over t. So if you have this type of spectrum, again you can see it is not satisfying the criteria. But what if this spectrum is a rect? So this will also be a rect. All these rects will be added, and again and then we will be able to satisfy the equation that the height will be maintained to be t. So under these conditions, you can only one x of t or x of f that can satisfy, and that will be that x of f is equal to t for f less than w. So for the whole value of minus w plus w, you have a rect of height t. In that case, its replica will also be a rect of height t, and all these rects, once they are substituted in a trained fashion, then you can see the height will be now constant to t, and hence the Nyquist criteria will be satisfied. So you will require your x of f to be of height t, and its width we just saw, f is equal to t is equal to 1 over 2w. So the width of the pulse is equal to 2w. So it is here, w here, this is also w here, and they're both rects. So the total width is 2w. So you will require a rect function in frequency whose height whose width is 2w and its height is t. So you can very well find the the time domain signal, because we know that sinc Fourier is rect, and if this Fourier is uh, in time domain, it is multiplied by 2w, then it means that frequency domain, its spectrum is scaled by 1 over 2w in magnitude, while in frequency it is scaled by 1 over 2w. This we have already seen in chapter 2. This comes to be like this. And if we say that 2w is equal to 1 over t, this becomes t over t, this becomes t, and you can write this as 2w, or you can also write this as ft. So the smallest value of t for which transmission with 0 ISI is possible is that t is equal to 1 over 2w, t is equal to 1 over 2w, and you are using a sync pulse, which is actually t over capital T. You can see here the function will be like this. So you will have all these replicas, but the replicas will be uh, just uh, attaching with the previous replica. There will be no gaps, and the height can be maintained to be t. Alright, so we have seen the case for non-zero ISI, that we should have a sync pulse in time, and frequency should be a rect, and that rect, when it is replicated, it satisfies the Nyquist criteria in frequency. As well, you can see it also satisfies the Nyquist criteria in time, because sync function is 1 at n is equal to 0, at t is 0, at all integral multiples of t, which can correspond to n t or intervals of sampling time. You can very well see the sync function is a 0 function, so it will satisfy the time and frequency domain. But there are issues with this sync function, and the major issue is its non-causality. You can see it extends from negative to positive values. And so this means that it will represent a non-causal system, which means it will become non-realizable, because you will need to require future values, so which is almost impossible. So how can we make it a realizable function? We say, all right, we use a sync, but we use a delayed replica of the sync, and we delay it to the extent and what we will do, so we will have the sync. In order to get rid of this non-realizability, of this non-causality, we will shift it by t naught. So we'll be actually delaying this. Once you'll be delaying this by t naught, you can see that x of t will be approximately 0 for a good value of t naught. देखिए ना, आपने इसको डिले किया, डिले का मतलब उसकी पीक वैल्यू 0 से लेके वो कहीं t naught पर जाके चली गई है. तो you can see that once you shift the sync in the positive axis, in the negative axis you will have still the sync, but lower values will be occurring. So we can neglect those, and we can say that yes, there is a proper sync, but we can very realize that it will have almost negligible values. So now as we are delaying this means definitely the sampling time will also be shifted by t naught. Previously, if you were sampling at mt, now you are sampling at mt plus t naught. Second difficulty is its decay. So sync decays slowly, decays by 1 over t. So hence, if there is some, let us say, mistiming, then you can see that you will have various syncs, and your infinite series of these syncs, and uh, such summation will not converge. Okay, So uh, this means it will diverge, so you will get a large value of ISI. So all of these factors are also written here. Case 2, it is possible to have 0 ISI, but you require these sinks. Alright, you can make them shift so that you can get rid of this non-causality, but still there will be a decay by 1 over t, and hence the conversion to 0 will be slow. Now the last case is when t is greater than 1 over 2w. In this case, this means that if you write this in terms of 1 over t, so t is greater than 2w, this means that 2w is greater than 1 over t, right? So remember that 1 over t is the rate at which the spectrum is being repeated. So if 2w, the total bandwidth of the original, and then the bandwidth of the replica, which is w by 2w, is greater than 1 over t, then this means that there will be overlap. You can see here that if one replica is standing here, let's say of bandwidth w, the other replica will be at 1 over t, which will be less than 2w. So hence you can have overlap, and this way you can design many solutions so that you have a spectrum which is of constant height t. So you will have infinite choices of x of f. You can choose various values of x of, so that the decay and the rise, they add in such a fashion so the height remains equal to t. One such pulse that the height remains t and using factor or raise cosine spectrum. Such pulse that can satisfy these conditions called the raise cosine pulse, and is defined as follows: from 0 to 1 minus alpha, the value of. So this is a famous raised cosine pulse. It is defined as follows. Here alpha could be a value from 0 to 1. For example, if I say alpha is 0, this will be 1 over t, 2t, so it will come out to be the second case. So f is 0 for f greater than 1 over 2t, and once alpha is 0, so this will totally vanish, no decay here. Alpha is 0, you can see that the frequency component is restricted to only 1 over 2t. So you can see here, if alpha is 0, then you have t till 1 over 2t. This term will totally go away because this will be 1 over 2t, this will be also 1 over 2t. So this range will not exist, and this will exist because greater than 1 over 2t, it will be 0. So this will come boiled to the second case. So alpha could vary from 0 to 1. Any bandwidth that is occupied beyond 1 over 2t, that will be called the excess bandwidth, and Nyquist frequency. For alpha is equal to 0.5, you can see this will be the response. So for alpha 0, you can see this is the same triangular pulse. For 0, alpha is equal to 0.55. We have these variations. For alpha is equal to 0.5. So you can see for alpha is equal to half, you will require half the bandwidth. You can just put here. If alpha is equal to half, this will be a 1 minus x will become a half. This will become 1 over 4. And if alpha is equal to half, you can see this will become half. This will become 1 over 4. And this will be again some value. So you will have a transition region. You will have a constant region, a transition region. And again, 1 plus half is 3 over 2. So at 3 over 40, you will have 0. So you can see the bandwidth has expanded, and that is why it is represented here. For alpha is equal to 0.5, your bandwidth will be greater as compared to alpha is equal to 0. And once if alpha is equal to 1, you will have the greatest bandwidth of 1 over t. So for alpha is equal to 1, you will have this 0. So for alpha 1, you can very well see this will be 1 minus 1 0 0, and 1 minus 1 is 0. But if we start from 0, this region will, there will be no constant region. There will be only this region starting from 1 minus 0 1 over 2t. This will be 1 plus 1 2, and just going up to 1 over t. So there will be a transition region from 0 to 1 over t, which is shown here. Access bandwidth for alpha 0, the bandwidth is 1 over 2t, is the same. The second case, and there is 0 bandwidth, access bandwidth. But for alpha half, you can see you will have half bandwidth. For alpha is equal to 1, you will have 100% bandwidth. So which means if you require another, previously Nyquist bandwidth is 1 over 2t, but you are requiring 1 over t, so you are requiring same amount of bandwidth. That is why the access bandwidth is 100%. Now the time domain version of this frequency domain expression is given as follows. This is a time domain version of the raised cosine pulse, whose frequency spectrum was shown here. I won't have time, just I will skim that this satisfies the this x of t, satisfies the Nyquist criteria. So if I put at t is equal to 0, cos of 0 is 1, this is totally 0, this becomes 1, this totally becomes 1, and sinc of 0 is 1. So you can see that our x of 0 is 1, so it is satisfied. And these are the various figures for alpha 0.5, for alpha 0, and for 1. So you can see in the book, a better diagram is there in the book here. This alpha is also called the roll-off factor. So you can see for different values of alpha, you have sort of modified things, and these values are shown. So we saw that for alpha 0, we will have a sinc. The symbol it will be 1 over t. For alpha is equal to 1, we will have 1 over t. This bandwidth will be equal to w. And even for this greater value of alpha, the decay is 1 over t cube. And even if you have some delay, the delay converges and get some finite sum. So what you will require, you will require our transmit and receive filter so that their overall response is a raised cosine filter. So our C of F, that is the channel response, let us say it's band limited to W we saw, so its width is 2W, so it will be given as follows, and it is 1. So your XRC or raised cosine filter response will be, GTF C naught F is actually 1 into GRF, this, and this is conjugate symmetric, or this is mash to GTF, this will become GTF mod square. Hence GTF mod square will be equal to under root of XRC E minus J2 pi F T naught. So, and you can, this is just there for, physical realizability, for causality, the large intervals choosing so that systems will be realized. And so GTF will be equal to under root like this, and hence I can say that the receive filter is conjugate symmetric to GTF. The same thing are also written in the book, you can find from the book also. So like this, and this is there for physical realizability. So this example, actually this was not done in the notes, but I think it is better that we do this now. This can be easily done from the book here. So he says that your frequency response of the channel, it is given as follows. So it is a band limited channel. The frequency response is up till it is band limited of 1200, or it means the bandwidth is 1200, and this is its frequency response, which is the linear. Roll-off factor is selected to be 1 over 2. So you are asked to determine the symbol rate. So what is the symbol rate, and then you can compare it with the Nyquist rate. So first of all, we know that the you can see this representation of my signal, my raised cosine pulse was like this, that it was 0 for once your f is greater than 1 plus alpha over 2t. All right, so I know that my alpha is restricted to 1200. So till 1200 it will be satisfying, but above 1200 it will not satisfy. For alpha is equal to half, because the bandwidth is 1200. So I will just put this value here, that 1 plus alpha 2t is equal to 1200, the boundary, and alpha is equal to half, 3 over 2 2t, this comes like this. So you can see, once you solve this, it's become 4 into 4 divided by 3, so 4 into 3 divided by 3, this becomes 4 into 4 is 1600. So 1 over t come from this equation comes out to be 1600 symbols per second. So then and the Nyquist rate, that is 2400 symbols because we know it is 12 because the Nyquist rate is 1 over 2t, or you can say it is 1 over w. Nyquist rate is given as follows, and w is equal to, this was case 3, that 2w is equal to 1 over t. So w is equal to 1200. This becomes 2400. So 1 over t is equal to 2400. This is a Nyquist rate. So we are not working at the Nyquist rate, but we are working at the frequencies at less than the Nyquist rate, 1 over 1600, so that we can have a practical and realizable filter. This I've discovered. We need this additional delay so that we have physical realizability, and the overall response has to be a raised cosine. So you can split the raised cosine filter between the transmitting and the receive filter. Another addition is that because you have a sink and a cosine, so even if you have a timing error, your intersimple interference converges to a finite value, unlike non-convergence for sinks. So we have found the Nyquist rate and we have this symbol rate, and so the frequency response will be like this. So the raised cosine function was actually, you can see, substitute the value of alpha everywhere, and you will get the raised cosine plus for your problem. So alpha is substituted as half. Once you put as half, this becomes 1 minus half, this becomes half, this becomes 1 over 4t, and then you know what is 1 over t. So we saw that 1 over t is equal to 1600. So this becomes, alpha is half, this becomes half, 1 over 4, and 1 over t is, 1600 divided by 4, this becomes 400. So that is why here he has put this to be 400. Okay. So you can also remind this become to 400, 1200, above 1200, you definitely know this will be 0. Or we know that there will be under root of x to c. And the phase can be chosen to be a linear phase. The second thing is that we design our signal so that we have a controlled ISI. So we allow a certain amount of ISI rather than having a strict condition. We allow signal design. For that case, design of dynamic signal with control ISI. So actually what we want. Problem is that when we have 0 ISI, then we just saw that we were transmitting at a rate 1 over t. But that rate 1 over t was less than the Nyquist rate of 2w. So it was coming out to 2400 symbols and per second, but you were sending only 1600 symbols per second. So your rate was less. So, but what if we allow the Nyquist criteria to relax? We say, all right, we can have uh, some ISI. In that case, we can transmit the signal at the Nyquist rate. At higher rate, we can transmit, especially at Nyquist rate, provided we allow some error or some redundancy at the SEO. So we relax and we will be able to get this 2W. Drawback is that you will have to allow some amount of ISI. So we know the condition is there for ISI, 0 SI you have to for 0 ISI you have to have x sanity 0 for non-zero values of n. For control ISI we will allow some other values of x, and by this allow and by this and by allowing this additional this ISI, we will see that we will be able to transmit the signal at the Nyquist rate. So one example is that x of n of t is not only 1 at n is equal to 0, but it is also 1 at n is equal to 1. Again, going to the notes because steps will be missing. This thing, all right. So we allow two values to be non-zero, not only x0 but also x1. All right, and you can see meaning of x1 was that you are allowing the last symbol am minus 1, as you could see here. Example, when I was allowing x1 was actually corresponding to am minus 1. So I'm not only allowing am, but I'm also implying that the ISI can also take into account the previous symbol that was sent. AM is the current symbol and AM minus 1 is the previous symbol that was sent, that is also existing as an ISI. So both are allowed. So x of n t is this. So what will be my z of n? So we have already seen that in our criteria the z of n is equal to t into x minus nt. This means the z of n will be equal to t, will be having a value of t at two values of n, which means that n is equal to 0 as well as n is equal to 1, which will now become minus 1 for z of n. So z of n will be existing at 0 and minus 1. So once n is equal to minus 1, so minus minus becomes plus 1. So at plus 1 it will be existing. So you will get this t value. It will be 0 elsewhere, but there will be two values, 0 and minus 1, where Zn will be equal to t. Then Z of n are the Fourier series coefficients. I can find my Z of f by putting in equation D, and this equation this equation D. So Z of n will be t for two values of n. For all other values it will be 0. This will be t for n is equal to 0, and for n is equal to minus 1 this will also be equal to t. So putting these values you will get your Z of dash dash will be equal to t for n is equal to 0, and then for n is equal to minus 1 this will be t, and but this term, because of minus 1, you can see in this equation. That this will n is equal to minus 1, this will become minus j2 pi f dash t. So you can also write this f dash or f same thing. So no problem. Finally, it has to be with respect to the frequency domain. F dash and f doesn't make any difference. So this will be my ZF or ZF dash given as follows. Now again for this case, you can see that if your t is less than 1 over 2w, or you can say the 2w is less than 1 over t, then again you can see that the Nyquist criteria is not satisfied as seen previously, because there will be gaps. Okay, because is existing after 2w, so that is why there will be gap between ww widths. But you can see here the best will be for t is equal to 1 over 2w. For t is equal to 1 over 2w, or at the Nyquist rate, we will see that the Nyquist criteria will be satisfied. And how can we see that? Just with the value of t is equal to 1 over 2w in this equation. T is equal to 1 over 2w, you can see that the ZF comes out to be this thing. And ZF, then ZF is actually replica of X of f. So the value of X of f for one time period, which was 1 over t, so X of f for interval of w will be totally this thing. Okay. And this whole term, it will be repeated for negative and positive frequencies, and then you can for f mod, and then you can repeat this for all other frequencies. They will not be all overlapping, right? And hence you get the answer. The f now, it is restricted to w, alright, and this is its x of its value. So I can just take this common, half of this common. This will become e minus j pi f over 2w. This will become e plus j pi over 2f. This will become a cosine, so I can write my x of f as this way. It is 0 elsewhere, but for f less than w, it comes out to be like this. So you can see, you take that common, and x of f comes out to be this thing. You can very well see from here. I took e minus j pi f over 2w common. This will become plus, this will become minus with 2, and this becomes a cosine. So your x of f is here. You can draw this x of f. So it is just a cosine from minus w to w. The phase and value. So I can also take, this is x of f, and then I can take its inverse Fourier, and so I will get the time domain version of this controlled ISI. So what is the signal? You can see the signal is actually in frequency domain, it is 1 over 2w, all right, with width of w, or you can say width of 2w, high value is 1 over 2w, and then another signal, again width is, you know, 2w, but its magnitude is 1 over 2w, while phase is e minus j by f over w. We have the frequency domain cosines, and this is how we can find the inverse Fourier of this thing. So you can see, you know, rect is sinc, or you can say that sinc is rect, but you can see that my rect is of width 2w. So you know that sinks with this scaling by 2w means that your rect is scaled by 1 over 2w, and amplitude is multiplied by 2w. So Fourier transform of the first term, width 2w, height 1 over 2w, which was actually here, height was 1 over 2w, and the width you can see is 1 over 2w, comes out to be sinc of 2w to t. And then, you know, this term can be received if I say that if I shift my sinc in time by 1 over 2w. Alright, so this means I will have to multiply in the Fourier by e minus j2 by f t naught, and t naught is assuming is 1 over 2w. So if I shift by 1 over 2w, so here I should multiply it by e minus j2 by f t naught, t naught is 1 over 2w, and 1 over 2w, this will become 2 cancels, minus yf over w, this becomes like this, and you can say this is a Fourier transform. So its time domain is this signal will come so I have the time domain version of the second term, so I add these two terms, and hence these two terms become the time domain version of my controlled ISI, where I allow one ISI term. This is also called the duo binary signal, where you have the condition that x and t is equal to 1 uh, for n is equal to 1 and n is equal to plus 1. Another signal could be that you allow for n is equal to 1 and n is equal to minus 1, because previously duo binary n is equal to 0 and n is equal to minus 1. Here it is n is equal to minus 1 and n is equal to 1, and this is called the modified signal, modified duo binary signal. This you can see here. So this we have proven, all the steps were shown. So but you can see here we were allowing x and t to be non-zero for 0 1, while for modified you apply it to be non-zero for minus 1 and 1. Again, you can do all the steps, and you will see that its x of t comes out to be these two things, and its Fourier comes out to be this. And its illustrated along with its x of t is illustrated here. So in general, I saw that I told you that you could have many choices of various signals that could be used to satisfy the Nyquist criteria, as well as to pass at the uh, Nyquist rate. But but the drawback is that you have to allow ISI, but as you increase ISI more and more, then the problem of controlling or getting rid of this ISI becomes cumbersome and impractical. This is general class. You can see you have some of these sinks. So we discussed as you saw the proofs, you just call this some. And in frequency domain, you have those your spectra that are shifted by some values. They are multiplied by some, in time they are shifted by values, and in frequency they are multiplied by the phasor constant, some phasor term. This is partial ISI. The advantage is that you can send the symbols at 2W, but you will have ISI, and then you have the techniques to get rid of this controlled ISI. So this completes our chapter 10. Chapter 10 is only till 10.3, so it is from 10, start from the starting of chapter 10 and it goes up to 10.3. Alright, this completes. So you will be going to the next chapter in the next lecture. That will be our last lecture. If you have any questions, you can ask. Alright, so I will end this lecture, and as I have told you already, the last chapter is about capacity. So we will skip this 11th chapter, go to chapter 12, which will be introduction to information theory. And so again, it requires 2 lectures to complete. So we will try to cover as much as possible. So we won't be able to cover the whole of it. So it has been decided we will cover it before the Shannon's theorem. So this part we will be covering. Yes, so we will cover up to 12.1. 12.2 section will not be covered. So this will be the total course of your the total course up to 12.1, which inshallah we will cover in the next lecture. So the course of the final, you can vary. So midterm course has already been explained to you. You can see the course of the final. So it will be starting from chapter 7 and will go to this section 12.1. I think no one has any question. I can stop the recording.